Hey y'all, welcome back. This week we're going to talk about nuclear power on another episode of Spin the Magnet. Right? Remember, really, fundamentally, that's kind of what we're doing here. So, in the case of nuclear power, really we're going to be talking about uranium. There are a couple of other ways to generate it, but like I have said in the past, I really wanted to stick to kind of the big picture stuff with this class. So the first place for us to start is to talk about what radioactivity means. And when we think about nuclear power, well, this is power generated from the nucleus of an atom. That is where a lot of the magic happens. And when we look at how energy is created by an atom, there's really actually two ways, although one of these is much more kind of easy to harness. So to talk about, well, we're going to talk about why energy can be, or how energy is essentially created from the nucleus of an atom. Generally, we're going to be talking about really big atoms, right? Uranium is a fairly large atom. But the discussion is actually pretty easy to understand if we look at something pretty small. So we're going to look at carbon as an example, get our head around the idea of isotopes. So carbon is atomic number 6, which means it's actually the 6th lightest element on the periodic table of elements. Number 1 is hydrogen, number 2 is helium, so on up to carbon. Number 6, oxygen, is actually number 8. So these are fairly small, these atoms have a fairly small mass. And what this number 6 means is it means that in the nucleus of that atom, there are two different types of particles in the nucleus, protons and neutrons. The protons carry a positive charge, so I've given a little plus sign here, and the neutrons have no charge. Overall, this is actually, the charge of this atom is then balanced out by the electrons, which are out here in electron orbitals. But an interesting way to think about a neutron is that it's actually essentially a proton that's captured an electron, is kind of holding it inside, so its charge is canceled out. We don't need to go too deep into the weeds there. So again, protons shown here with little plus signs, neutrons shown with the number n, and we're kind of just looking at regular carbon. So carbon is atomic number 6. Actually, in that sense, carbon is just kind of a nickname, right? We say the word carbon, but we could say atom of 6 protons in its nucleus, but that's not very effective to say, so we give it a nickname: Jeff, Steve, carbon. It's all kind of the same. But if we think about normal carbon, and we'll kind of revisit what that term means in a second, each of these protons, the mass of that proton is balanced by a neutron. So we have to start thinking about the force that's holding this nucleus together. So the force that holds the nucleus of an atom together is essentially an electrical force, kind of like an electromagnet. Again, we can say the details for a physics class, but it's the strength of that force is related to how many protons are in there. So in this case, 1, 2, 3, 4, 5, 6 protons in our carbon atom. So that's the strength that's holding it together. And then I drew an isotope of carbon, which in this case would be kind of regular. And each proton has its mass balanced by a neutron, which means that overall it has 12 particles in its nucleus. So its atomic mass number, which is different, is 12. And the way that we would write that if we were taking a chemistry class would be carbon 12. Now that's not the end of the story, right? Most carbon that occurs as carbon 12. About 99% of carbon is carbon 12. But in other cases, there's an extra neutron. And in the case where there's an extra neutron, the atomic number doesn't change, right? Because we still have 6 protons. If it doesn't have 6 protons, it's not carbon, right? That's the definition of carbon. But here it's got an extra neutron, so it no longer has 12, it actually has 13. So a little bit shy of 1% of carbon as it naturally occurs is carbon-13. And then as we start to kind of build out the nucleus even more, if we add another neutron, we get to a fairly famous isotope, probably the most famous isotope in the world, carbon-14. Meaning it has 14 particles, and it actually has 2 extra neutrons. And so at this point, what we start to see happen is the mass of the nucleus is getting bigger and bigger and bigger, right? It's gaining particles, right? So carbon-14 is actually heavier than carbon-12, but the strength that holds that nucleus together hasn't changed. The strength is related to the atomic number, how many protons. And so if you've ever made, I always compare this to a meatloaf. If you've ever made a meatloaf, you have meat and you have breadcrumbs, and you've got some eggs and some other things like that that bind it together. But if you start adding too many breadcrumbs, you're not adding anything that will bind it together, you're just adding filler, and eventually your meatloaf is going to start to crumble. In the case of carbon-14, there are too many breadcrumbs in the meatloaf, and this is an isotope that we would term, carbon-14 is considered unstable. Unstable in the sense that its nucleus is crumbly, and it will break apart. It will essentially crumble. It does it in a very specific way, and that is what we call radioactive decay, right? That's another term that we might use is fission. So something that is going to break apart undergoes fission, right? Actually, we can kind of back off for a second and look at some of the ways that we do get what the energy is created from atoms. So when an atom breaks apart or undergoes what we just talked about, fission, right? So fission is breaking apart. The opposite of fission, which we'll talk about in a second, is fusion. So when an atom undergoes fission, as you can see here in this diagram, this is showing, one, it's not really a hypothetical atom, but you can see one neutron is kind of added, hits that nucleus and joins it, and that nucleus then breaks apart or splits into smaller and smaller pieces. It releases some neutrons, some other atomic particles, and energy, right? So there's this is kind of what E equals mc squared is all about, right? Energy can't be created or destroyed. So when we undergo fission of most types, the atom breaks apart, produces smaller particles, and some energy. For smaller atoms, the opposite is true. Actually, if you have 2 atoms, famously hydrogen, and this is how a sun works, in the guts of a sun or the guts of a star, it's mostly hydrogen, and there's enough pressure that inside of that star, those atoms are being forced together so hard that they actually will fuse together and become a new, more complicated atom. So if you take 2 hydrogens and squish them together really hard, you get a helium atom and free neutrons and energy, heat, right? Energy in the form of heat. So both nuclear fission and nuclear fusion, as you can see here, produce energy. Although we would love to be able to carry out fusion energy, that's usually what people see as like the type of thing that would just fundamentally change the world, right? So if you were to take 2 hydrogen atoms, smash them together, extract that energy, use it to turn on the lights and things, the byproduct is actually helium, which we could even bottle and sell. But you were talking about building a star on Earth, and we're not able to do that. The French are getting close, right? There's a lot of people who are interested in doing this, right? Of course, you'd change the world. You'd solve all of our energy problems, but we're not there yet. So, at least as far as we're going to talk for the rest of this discussion about nuclear power, we're talking about fission, which is definitely dirtier, but it's natural decay, right? Remember, splitting apart that creates energy. We're going to take energy in the form of heat, and we can take advantage of that heat to create power.